and its options, this equipment. Okay, so tympanogram is a graphical representation of dash versus dash.
Admittance versus pressure.
Yes, admittance against pressure, right? Okay, so it's understood that for doing this we need to have a pump, right, which varies pressure, and we need to have an admittance meter which measures admittance at different pressure points. You understand? Okay, so the type of technique what we use here, okay, if you want to say technically, we can call this as sweep pressure. Why? Because we are changing, not just using one pressure, actually we are sweeping the pressure. You understand? Okay, so for sweeping pressure we need to have a start point and a direction. Right? Okay, so both are defined here. So you can see this. So pressure is defined by its rate, right? Okay, so its rate is from 12.5 to 200. Okay, so actually we can do at the highest rate in this equipment, that's 200. Why? Because the rate of pressure change has got no influence on the tympanometric findings. You understand? So there is no point doing it slow or fast or anything. You understand? So ideally doing it fast saves time. Okay, so we set the rate to 200. By default in this equipment it is 50, right? But it is not mandatory that you have to do that 50. You can change it to 200. But the pressure sweep direction has got a serious effect on tympanometric findings. And you can define the effect as hysteresis, right? Hysteresis means the peak will be obtained on the direction of sweep. That means, okay, so as you sweep from negative to positive, you will see positive peak. And if you sweep from positive to negative, it's more likely to, the peak pressure will shift to negative peak or towards negative side. This is relatively negative. It's not, it doesn't mean that it is minus, relatively negative. You understand? Okay, so we have to carefully select plus or minus, or whatever tympanogram we borderline obtain, say for example minus 100, which is close to C-type, and you tend to diagnose it as C-type. So in those instances you have to check whether this is a real incision tube effect or it is because of pressure sweep direction effect. Understand? How will we do? By changing the sweep direction. So we can choose from minus 600 to plus 400. So wide range is given. Okay, so in this case, as of now, we will not be changing it until unless there is a need occurs. We can start from positive pressure to avoid clinically discomfort for the patient. Building a negative pressure all of a sudden will cause a lot of discomfort for the patient, especially for those people who have vestibular disorders, right? And it will be discomfortable for anybody. Okay, so generally we prefer doing it at positive, but when a need occurs, we need to cross-check. You understand? Okay, so now what we have to do is, okay, so and you see two graphs here. Okay, so the one is pressure, the one's on the top, and the other one is complaints. So both of the complaints change as we change the pressure. How the complaints changes can be observed even in this graph and also in this meter. You understand? But only the range is very small. So if it goes out of this, it will get stuck here, right? Okay, so you won't be seeing any movement after that. So you might think that okay, the graph is otherwise the measurement is stopped, but then actually it's beyond this range, okay, scale. Okay, so still the impedance meter might be measuring it, okay, but then you won't be seeing it on the scale. Okay. Then other than that, you have baseline on and off. Okay, so baseline means compensated and uncompensated temperature. Okay, so if we say baseline on means compensated, if we say baseline off means uncompensated. The difference between compensated and uncompensated tympanogram is ear canal wall, right? Okay, so and you can make out from the tympanogram as such by looking at it, right? If it is an uncompensated tympanogram, you don't find volume will be red over there. Okay, but then if it is uncompensated tympanogram, then your compliance graph or the tympanogram will not start from 0, right? It will start from a positive value, right? Okay, so what is going to happen? The pump is going to initially start from plus 200, so it builds a positive pressure in the air canal, right? And then sweeps 200 times per second, right? Okay, and goes till minus 200. In 200 times per second, okay, at every interval, right, at every in-between pressure, it's going to measure compliance. Okay, so on those compliance will be a line drawing, will be joined, like how our audiogram connects all the points, like that will be connected. So you will see a single graph. Okay, so now what happened is we saw our graph quickly going from one side to the other side, and then a symbol came hold, right? Because it's still maintaining at minus 400 hertz. The press is stuck at minus 400, and still the compliance is less. So you can see that it's within the scale. So you can see that the compliance changed from 0 to somewhere around a minus value. Understood? Okay, so now when you stop it, okay, so this graph retains. Okay, so then what you have to do is you can see the values appearing automatically. Okay, so if you see the next time, see carefully what's the first value comes on the screen. What's the first value appeared on the screen? Yes, why? Because air canal volume is calculated based on what pressure? Start pressure, right? So regardless of plus or minus, okay, you will see the start pressure, the air canal volume appearing first. Say for example, now we started at plus 200. Imagine we are starting at minus 400. See first value, air canal volume. Do you understand? So regardless of whichever direction you sweep, you will see air canal volume is the first value what appears. That's a procedure. Okay, so we use the method of pressurizing the air canal first to extreme positive or extreme negative, okay, and then considering that compliance as air canal volume. Okay, so the air canal volume is the first procedure to be completed on the tympanogram procedure. Okay, so that's the first value what appears. Once that value is calculated at the extreme pressures, and then that value is subtracted out from the rest of the values, right? Rest of the values. So the graph appears like this. And did you also see the air canal volume changing between negative side and positive side?
Yes.
Which was more? From positive side to negative side was more. And also did you see the DAPA? This is minus 10 now. Okay, so if I change it to minus 400, you see what happens. Zero. So this is what I told as pressure effect, right? So as the direction of sweep changes, you will find the peak pressure changing. Suppose if it is because of some pathology, right? Okay, which is crossing borderline values between C type and A type, right? Things like that. Then you've got to check whether it is really sweep effect, pressure direction effect, or it's because of pathology. Okay, and you can see that compliance. What is the compliance rate? 0.6, right? Okay, so how did the 0.6 come from? Maximum
admittance.
Maximum
Admittance of the
admittance. Where is the maximum admittance here?
0.0.
The instrument uses a technique called peak picking, right? Okay, peak picking means wherever there is an peak, it considers that as static compliance or the highest positive value or highest compliance. Okay, so it is assumed that at peak pressure is the highest compliance obtained. Suppose because of any methodological error, slightly shake the tube probe while I do the test. Okay, so now did you see that there is one more peak here, right? Because this is because of leak or some movement. Suppose if this peak is now, in this case, this is shorter than the peak confines. In case if this is taller than the peak compliance, then it will consider that as peak compliance. So it uses only one method as peak picking. So if in your graph, okay, you might very well know that this is an artifact and your peak compliance is somewhere down there. Okay, but still if you read only the values, then you will be biased by writing the values as a different error values. In the sense you will be plotting the artifact compliance rather than the original. So in that case what you have to do is you have to use cursor. So select cursor, then you can manually measure. You can see this. This is the pressure and this is the compliance at the cursor, right? So when you go down, so you can see that. You can see that it is. When I keep the cursor at that point, okay, I can read 0.05 and -10. You understand? So this is approximately the same value what is detected by the system as peak. You understand? 0.53 and -15. So my cursor also reads -15 and 0.53. So this is the place what instrument detected as peak compliance. You understand? Okay, so now suppose in many cases if you measure it manually, you will avoid all this confusion. Suppose in this case artifact is not so big, still we detected the correct peak compliance, so it's fine. Otherwise we have to use the cursor. You understand? Like in the previous case where the pump was leaking, so even when you see from negative to positive, you got multiple peaks. So in those instances, you have to use the cursor to measure the actual compliance. Okay, so now we will switch off the baseline and we will see what happens. See that the compliance graph doesn't touch zero. It doesn't start from zero. It starts from somewhere. What is the value it starts with? Can you tell me exactly? There is a clue here in the screen itself.
Starts from 1.
How did you say it? Because it's closer to 1?
No, sir.
Air canal volume. Yes. So air canal volume is the starting compliance. You understand? Because that is what got subtracted. You understand? Okay, so when you go take the cursor, right? If you measure the compliance at the base of it or at the starting point, can you see 1.07? Right? So that is what is detected as 1.1 as air canal volume. Do you understand? Okay. So now this is the difference between compensated and uncompensated. The compensated would start from 0. The 0 is equal to air canal volume. So air canal volume is, suppose if you consider air canal volume as A, then A is equal to 0. Understand? Then every time you subtract A from all the points. Do you understand? Say for example, easiest one would be finding out air canal, the peak compliance. Previously obtained peak compliance was 0.6. So in this case, did you see it is 1.6. This is the total compliance. So 1.6 minus 1.1 is what is the value what you would have got under compensated. Did you get it? We can do this manually without having any sweep direction or without having any sweep rate. Right? Do this manually without having any sweep direction or without having any sweep rate. Right? Okay, so you just press the button manually on the lower panel and it starts from 0. So you can decide what direction you want to sweep and with whatever speed you want to sweep. Suppose now I am doing from positive to negative. At the same time, now I am doing from negative to positive. Did you see how the peak shifted? So this is what is the direction effect or pressure direction effect. You see how many ever times I sweep from both this direction. Both these tympanograms will not overlap. and downside there is an arrow mark which indicates which direction I am sweeping currently. See that? Okay. So if you do it manually, right? Okay, so you have two tympanometers here. So both of these values are depicted here. So one is minus 25 and one is plus 15. In this case, minus 25 to plus 15, the direction effect is really huge, right? Because almost 35 to 40 decapascal difference is because of direction itself. More, okay, so you got some more options, right? So that is, you got probe hertz. So you got what component you want to measure, and it is saying what range you have to measure. Here is just for the sake of recording, that is printout, that you want to record it as right ear's value or left ear's value. If you are noting it down manually, this becomes not so important. So you can change different frequencies. What are the frequencies available?
678,000.
226,
678.
678, 1000. And what are the different components available?
Susceptance, BG.
Components in this instrument, actually though you have got different components making out the total tympanogram or total impedance values, measuring some components makes some sense. In this case we are measuring only Y. So why we are measuring only Y? Y is total admittance, right? So we are measuring total admittance by measuring only one component of the 6 components, whatever constitutes total to the impedance reaction. And what is that component?
Susceptance.
Under that you have got 3 each. Out of which, what is this Y? Is it the total of all? Is it the total of all?
It is a total of reactance components.
It's a total of Is it a total of all or not? It is a total of only one, and that is stiffness susceptance. So we measure it as compliance. Otherwise, we will not be calling this component as compliance. You understand? What do you mean by compliance? What's the opposite of stiffness? Right? So we are measuring in terms of admittance. So the stiffness is called as compliance. You understood? So that's why we use the term. It's quantified in terms of compliance. So compliance means it's only one component out of all the 6. This holds good only when the tympanogram, whatever we are taking, is with very low frequency, that is 226 Hz, the lowest frequency available in the equipment, and if the middle ear is stiffness dominated, or if the middle ear pathology is altered, it should be stiffness dominating pathology. Do you understand? Should be stiffness dominating pathology. Only then that will hold good. Do you get it? In any of the other cases, you got to change the probe tone frequency, right? And you have to measure more than one component. So these are the components of it. You can measure Y. Y is total admittance, or you can measure total susceptance by recording B, or total conductance by recording G, only G, right? Or you can plot both of them against each other, that is B and G, right? So instead of doing it independently, we do it together. Which one? B and G. Why? Because B and G, the interpretation is in terms of, not in terms of writing down an audiometric value, because we do have no normators for B and G components, whatever we record for clinical patients. We have normators probably for normals, but not for clinical patients. So we will not be recording it. So what the concept we use for recording B and G is where B is high, G is low. Where B is cancelled out, that's where G takes over. We call that as resonance. Right? We call that as resonance. Right? Okay, so to find out that, you need both B and G. So instead of finding out B separately and then G separately and then plotting two different graphs and then interpreting it, we plot them at the same graph. Okay, so either we do Y or B and G. But you have options also for measuring B separately and G separately. So at this point we are measuring only Y. And what is the component we are measuring? Total Y means total admittance. Okay, but in this case Y is equal to stiffness susceptance. So we call this as single component tympanogram. Right? We call this as single component tympanogram. Why? Because we are measuring
Only one
only one component, and that component is stiffness susceptance. Is that understood? Right. So if you measure more than one component, that is susceptance and conductance. You understand? Susceptance and conductance. Then you call that as
multi-component.
You understand? You're familiar with those options, whatever is there on the screen, and how does that influence, right? So you cannot use very static values for each of patients. Or whatever patient comes, you cannot use the same settings, right? You've got to change the settings in order to get the correct interpretation, right? Or if you want to find out the pathology correctly, so you've got to use all these options, not just one standard options like how you usually do tympanogram, call the patient and sit, right? Make him sit and press start. Do you do anything other than that? Actually, you've got to learn all this so that it will help you. So now this is the biggest error what we do in tympanogram finding, considering direction effect as pathology. Do you understand? Considering direction effect as pathology. So what have we done now? Tympanogram, what is it? It's a graphical representation of. When you say complaints, you should understand what is the component you are measuring, right? What's a component?
Stiffness
Stiffness susceptance. So you're measuring stiffness susceptance, the only component what you measure, and you consider that as the total admittance, because the rest of the components are negligible contribution to it. Because so, and then you sweep the pressure, and then you find out change in the components, and you look for two values. First, air canal volume. Measure the air canal volume, consider it as X, and subtract it out from the rest of the values, right? And then you plot a final graph, which is the actual susceptance or the complaints of middle ear, right? That's the actual complaints of middle ear. After plotting the graph, what do? You go for identifying peak, right? Go for identifying peak. So what does the peak means? That is the static pressure, right? Static component, that is the highest component. Why we call a static component? You can consider it as peak complex, right? But then we call it as static complex. Why we call it as static complex? Because we are obtaining it at the static pressure. Or what do you mean by static pressure? You can say like that also. Any other way? Zero. What do you mean by static? That is
constant.
The middle ear is at rest. Can you call resting as static? Yes. So you call static complex because we do this measurement at the static pressure, and you consider static pressure is the pressure what the middle ear is, or tympanic membrane is at rest, right? Or rest of the values. Then why do we measure rest of the values for? We need two values. One is air canal volume. That's at the start pressure, and then at the peak pressure.